Section: Introduction. In this section, we discuss how chain of thought (COT) prompting has significantly improved the reasoning abilities of large language models (LLMs). By providing clear reasoning steps, COT allows these models to express their thought processes in a structured way, enhancing their capabilities in mathematical reasoning, logical deduction, and problem solving. However, we note that COT struggles with complex spatial reasoning tasks. Recent research has adapted COT for multimodal models using two main strategies. The first involves a two-stage process where image information is extracted through techniques like captioning or bounding box detection before reasoning occurs. The second approach uses React-style pipelines that incorporate external tools, such as code interpreters, to gather visual data. While these methods can handle both text and images, they rely heavily on separate visual components, making them less effective for advanced spatial reasoning tasks. We recognize that human thinking goes beyond just language, as we can seamlessly process information in both verbal and visual forms. This dual coding theory suggests that we use both verbal and non-verbal channels for reasoning, which is essential for decision-making. For example, we often create and manipulate mental images to understand our surroundings and visualize outcomes. In spatial reasoning, we observe that LLMs and multimodal language models, MLLMs, tend to think only in text, which we refer to as verbal thinking. To address this, we introduce the visualization-of-thought (VoT) approach, which uses textual representations as mental images in spatial reasoning tasks. However, VoT has limitations, including its reliance on text alone, which can hinder performance in complex multimodal tasks where visual details are crucial. We question whether MLLMs can truly reason in a visual context, beyond just using text. React-style methods generate visual thoughts using external tools, but we argue that this does not equate to the model itself reasoning multimodally, as the tools limit expressiveness. We also highlight recent advancements in multimodal generation, where models can produce outputs in both text and visual formats. This progress has led to the creation of sophisticated systems like Chameleon, Transfusion, Gemini 2, and Latent LM, which excel in interpreting and generating high-quality outputs across modalities. Building on these advancements, we propose the Multimodal Visualization-of-Thought (MVoT) framework. MVoT utilizes multimodal native architectures to integrate visual and verbal reasoning, allowing models to generate visual representations of their reasoning processes. This approach enhances the clarity of reasoning and improves both the quality of reasoning and model interpretability. In our work, we implement MVoT by fine-tuning the Chameleon 7B model. We introduce a token discrepancy loss to improve visualization quality during reasoning. We validate MVo's effectiveness through extensive experiments on three dynamic spatial reasoning tasks: Maze and MINIBEHAVIOR, which focus on spatial interactions, and FROZENLAKE, which emphasizes pattern recognition in dynamic settings. Our results show that MVoT outperforms traditional COT by over 20% in challenging scenarios. In summary, our main contributions include the introduction of MVoT as a novel reasoning paradigm that combines text and vision, the implementation of MVoT in Chameleon 7B with token discrepancy loss, and comprehensive experiments demonstrating MVo's superior adaptability and robustness in complex spatial reasoning tasks. Section Summary. In this section, we introduce Multimodal Visualization-of-Thought (MVoT), a novel reasoning paradigm that integrates text and visual modalities to enhance reasoning processes in large language models, LLMs. We demonstrate that MVoT, implemented in Chameleon 7B, significantly improves performance in complex spatial reasoning tasks by generating visual representations of reasoning traces, outperforming traditional chain-of-thought methods by over 20%. Section: Multimodal Visualization-of-Thought, MVoT. In this section, we introduce Multimodal Visualization-of-Thought, MVoT. We recognize that humans often create mental images to aid in decision-making. Instead of using text to represent these mental images, MVoT allows models to generate visual representations as part of their reasoning process. By integrating both verbal and visual thoughts, this approach provides a more intuitive and effective way to understand multimodal reasoning. We define the MVoT process as follows. Given a sequence of multimodal inputs, our model generates a mix of verbal and visual thoughts during reasoning, ultimately leading to a final answer. We denote a pre-trained multimodal language model, MLLM, with parameters, and we represent the multimodal input sequence, verbal thoughts, and visual thoughts as different variables. In tasks requiring multiple reasoning steps, we use a method called chain of thought, COT, prompting to create intermediate verbal thoughts based on the inputs and previous steps. The final output is derived from all these steps. MVoT enhances this by adding a visual representation to each verbal thought, allowing the next step to be influenced by both prior verbal and visual thoughts. To equip MLLMs with MVoT capabilities, we train the model using multimodal inputs and their corresponding outputs, which include both verbal and visual rationales along with the final answer. This training helps the model learn to interleave verbal reasoning with visual thoughts, improving its ability to tackle complex reasoning tasks. Next, we focus on autoregressive MLLMs that use discrete image tokens for training and inference. However, MVoT can also be adapted to other model types and modalities as long as they support interleaved multimodal generation. For multimodal sequence modeling, we adopt the chameleon architecture, which utilizes a unified transformer to handle both image and text tokens. This architecture employs two tokenizers, one for images and one for text, converting them into discrete token sequences. The image tokenizer encodes images into a sequence of tokens, while the text tokenizer does the same for text. These token sequences are then combined and processed by a causal transformer model. We denote the MLLM's codebook and its dimensions, along with visual codebook indices and embeddings. The predicted values are marked with a hat symbol. To address the issue of discrepancies between separately trained tokenizers, we introduce a token discrepancy loss into the autoregressive MLLM framework. This loss helps align the language modeling and visual embedding spaces while maintaining gradient integrity. The token discrepancy loss minimizes the differences between predictions and actual labels in the visual embedding space. We calculate a similarity matrix to assess the relationships among image tokens, using mean-squared error to measure similarity based on pairwise distances. The model predicts a probability distribution for each image token, and the token discrepancy loss penalizes significant deviations from the corresponding labels, aiming to improve the quality of generated images. Section Summary. In this section, we introduce Multimodal Visualization-of-Thought, MVoT, a reasoning paradigm that enhances decision-making by generating image visualizations alongside verbal thoughts, allowing models to process multimodal inputs more intuitively. We also discuss our training approach for autoregressive MLLMs, which incorporates token discrepancy loss to improve the quality of generated images by aligning visual embeddings with their corresponding labels. Section: Training. In this section, we fine-tune the causal transformer model using a next token prediction approach, keeping the image and text tokenizers unchanged. We utilize a loss function that combines token discrepancy loss for image tokens and cross-entropy loss for both text and image tokens. For our spatial reasoning tasks, we focus on three dynamic scenarios that require the model to locate objects, understand environmental changes, and predict outcomes based on actions. We ground these tasks in grid-based environments: maze navigation, installing a printer from MINIBEHAVIOR, and FROZENLAKE simulation. Each task presents different complexities, reflecting real-world abstractions. In the maze task, we provide the model with an initial maze image and the agent's starting position. The agent must navigate to a destination, following a sequence of actions and predicting the final location from options labeled A, B, C, or D. For the MINIBEHAVIOR task, we choose installing a printer, where the agent must find a printer, pick it up, and place it on a table. The printer, agent, and table are represented by specific symbols in the environment. The model predicts the outcomes of the actions, such as whether the agent successfully picks up the printer or if any objects are missing. The FROZENLAKE task, inspired by a previous implementation, involves navigating a grid-based frozen lake. The agent starts at a designated position and must reach a goal without falling into holes. The model determines the consequences of following a sequence of actions, with this task featuring more complex patterns and details compared to maze and MINIBEHAVIOR. For our experiments, we create datasets for these three spatial reasoning tasks, each with varying complexities. We present dataset statistics and detailed data collection methods in the appendix. We structure the data as interleaved text-image pairs to train our model, MVoT. We use the MLLM model as our backbone, which is well suited for generating interleaved text and image data. We tune part of the model's parameters using LoRa on MI300X for 40 epochs, focusing on optimizing the prediction loss. We also evaluate the performance of GPT-4o using zero-shot inference, chain of thought, and MVoT in a React-style pipeline. We provide detailed prompting templates and hyperparameters in the appendix. We compare MVoT with several system variants: direct prompting, where the model outputs choices directly; chain of thought, which involves step-by-step reasoning; and interleaved training, which calculates loss only on text tokens. In contrast, MVoT computes loss across all token types. We summarize the comparisons among these variants in a table. Section Summary. In this section, we fine-tune a causal transformer model using next token prediction while keeping the image and text tokenizers frozen, and we introduce a loss function that combines token discrepancy and cross-entropy losses. We evaluate the model's performance on three spatial reasoning tasks: maze navigation, installing a printer from MINIBEHAVIOR, and FROZENLAKE, each designed to test the model's ability to navigate and interact within grid-based environments of varying complexity. Section: Metrics. In this section, we extract the predicted answer from the model's output by looking for the phrase, "the answer is." We calculate accuracy for multiple choice questions by comparing the predicted answer with the correct one to see if it is right. We equip our proprietary models with MVoT. Instead of relying solely on a single 7 billion parameter open-source model to generate multimodal thoughts and answers, MVoT can also be used as a plugin for other proprietary models, including those available through APIs. We provide GPT-4o with visual thoughts generated by the fine-tuned MVoT model after it produces verbal thoughts. We observe an improvement of over 15% in accuracy across all tasks, as shown in our table. We hope this work encourages further exploration and advancements in multimodal reasoning with multimodal thoughts. In summary, MVoT shows effective performance and better generalization than the chain of thought method in spatial reasoning tasks. Regarding visualization quality, we note that during training, the model creates the next visual thought based on the previous ideal image. In contrast, MVoT generates multimodal thoughts, including text and images, based on earlier thoughts, highlighting the difference between these two methods. We refer to these as image editing and MVoT in our discussion. Since MVoT relies on recursive generation, we focus on the quality of its visualizations in this section. For qualitative analysis, we present examples of both correct and incorrect images generated for the FROZENLAKE task. More visualizations can be found in our figures and appendix. We categorize visualization errors into two types: 1. Wrong visualization, where the generated image is incorrect, and 2. Redundant patterns, where unnecessary visuals appear outside the intended modification area. We also notice that as the complexity of patterns increases in FROZENLAKE, the details in generated images often become blurred compared to those in maze and MINIBEHAVIOR. Background details in FROZENLAKE visualizations frequently show minor inconsistencies, and similar differences arise between original and reconstructed images. This variability often leads to a loss of fine details, highlighting the limitations of multimodal large language models, MLLMs. These findings indicate a need for further research to enhance the quality of image tokenization and generation in autoregressive MLLMs. For quantitative metrics, we define automatic evaluation measures based on the types of errors we identified. Visualization accuracy measures how accurately the intended modifications are visualized. Visualization pattern redundancy assesses unintended visuals outside the target area. Visualization correctness step looks at the average length of the first few correct visualizations in a sequence. And visualization correctness ratio calculates the average proportion of correct visualizations in the action sequence. Due to the complexity of FROZENLAKE's images, we only report quantitative results for visualizing agent positions in maze and MINIBEHAVIOR. We find that using token discrepancy loss improves accuracy and reduces redundancy in visualizations. Our table shows that MVoT, enhanced with this loss, achieves about 95% accuracy in generating correct visualizations during reasoning. Without this loss, the quality of generation declines significantly, leading to more redundant patterns and inaccurate state transitions. These results are consistent with our findings in the image editing scenario, as shown in our figures, which track metrics for maze over different epochs. Additionally, poor visualization quality negatively affects task performance, as indicated in our table, underscoring the importance of high-quality visualizations for better outcomes. We also observe a performance drop in FROZENLAKE without token discrepancy loss, from 0.8560 to 0.7260. Our empirical evidence suggests that incorporating visual embedding with token discrepancy loss, along with another loss type, helps improve visual generation quality. This aligns with previous findings that noted similar issues in embedding alignment for MLLMs. We discuss further insights into embedding discrepancies in autoregressive MLLM architectures in our later sections and figures. Section Summary. In this section, we evaluate the performance of our MVoT model in generating multimodal thoughts and visualizations, demonstrating over 15% accuracy improvement when integrated with GPT-4o. We also identify key metrics for assessing visualization quality, revealing that incorporating token discrepancy loss significantly enhances accuracy and reduces redundancy in visual outputs, which is crucial for effective task performance. Section. MVoT complements COT in reasoning. In this section, we explore how MVoT complements COT in reasoning. To determine if MVoT and COT have similar reasoning abilities and fail on the same data, we combine their predictions and assess the best possible performance. A data point is deemed correct if either MVoT or COT provides the right prediction. Our results show that the combined performance nearly reaches 100% accuracy on maze and MINIBEHAVIOR, and 92% on frozen lake. This indicates that MVoT enhances textual COT by offering a different reasoning approach, allowing us to improve overall performance through a combination of methods. Next, we examine how token discrepancy loss helps improve the quality of generated visual thoughts. We look at two types of embeddings used in autoregressive MLLMs: token embeddings for language and visual embeddings for image tokenization. These embeddings come from separate systems, which can lead to differences between them. To assess their alignment, we compare the embeddings from Chameleon, LVM, and Llama Gen by measuring the overlap of similar tokens. Our findings reveal that, on average, only one token overlaps among the top 10 similar tokens, and about 20% overlap among the top 50. To illustrate this issue, we replace image tokens with their closest matches in both embedding types and reconstruct the images. After several iterations, the reconstructed images show significant differences from the originals, highlighting the misalignment. By introducing token discrepancy loss, we aim to improve the alignment between visual and token embeddings, which should enhance the quality of visual reasoning. We also discuss multimodal chain-of-thought reasoning. COT prompting has significantly improved the reasoning abilities of LLMs. Recent studies have explored various methods to adapt COT for multimodal models. Some approaches use a two-stage process where image data is first converted into text or structured formats before reasoning. Others employ React-style pipelines that integrate external tools for processing images. While these methods effectively handle both text and visuals, they often depend on separate visual modules, limiting their expressiveness. To overcome these challenges, we propose MVoT, a new reasoning method that utilizes multimodal understanding and generative capabilities. MVoT allows for the generation of interconnected reasoning across different modalities, leading to a more cohesive and flexible approach to multimodal reasoning. In the realm of multimodal spatial reasoning, we focus on understanding spatial relationships among objects and their interactions with the environment. Despite progress with LLMs and MLLMs, this area remains challenging and is gaining more research attention. Recent benchmarks have been introduced to evaluate multimodal spatial reasoning, but few studies have examined how actions affect spatial layouts, which requires dynamic imagination and state tracking. Various methods, like spatial VLM and spatial RGPT, have been proposed to enhance spatial reasoning using 3D data. However, existing approaches often overlook the potential of multimodal native models to visualize spatial dynamics. Our method integrates text and vision within reasoning traces, improving interpretability and robustness by generating mental images that align with spatial reasoning. Finally, we discuss video generation world models, which aim to predict future events to better understand the world. These models focus on generating videos to simulate real-world dynamics. Recent advancements in generative models have significantly improved our ability to capture motion and physics. The Sora model has shown remarkable performance in this area. World models extend beyond visual synthesis into various fields, including robotics and autonomous driving, by simulating physical interactions and predicting environmental changes. While previous work typically generates outputs in a single modality, our MVoT introduces a new reasoning method that supports multimodal generation, enhancing our understanding, reasoning, and simulation of complex scenarios.